Okay, so that's done. Our speaker tonight is Alan Witzgall. He is senior optician for Esco Optics in Oak Ridge, New Jersey, and he will be speaking on glass, the power behind discovery. Alan?
Thank you. Thank you. Good evening. Thank you for coming out on this rather rainy night. As Wayne had just mentioned, we're going to be talking about a material that is pretty ubiquitous around the world, particularly in science. And those of us that use telescopes usually know little about the properties and the incredible technology that's behind the most common material. So let's see just how it was discovered, modified, and still is valuable after 5,000, imagine that, 5,000 years of use. This is incredible. Okay, so first up, what is glass? And according to the SPIE handbook, which is what the opticians always use and engineers, it's defined as glass as a non-crystalline amorphous solid that has This is Weber desert glass. It's from a Libyan crater, of the Weber crater, circa about 4500 BC. We believe that this had been known maybe even earlier than that. And interestingly enough, the Egyptian necklace that you see over there, that was found on Tutankhamun when they discovered his tomb and such. And in the middle of this is a scarab. You can see it right there with the wings going up on it. That is made of this Weber desert glass. And by the way, the desert glass itself, the Libyan crater I'm talking about is not a volcanic crater. This was an impact crater. Something came in, crashed into the ground, and the heat from the collision formed all this beautiful, actually, yellow glass. Okay, but not to be dissuaded, the Egyptians themselves learned how to manufacture at least a crude form of glass and even created glass blowing. You can see on the far right over there a flask, I guess we would call it, that survived all this time. Okay, and of course it exists in nature. If you have a lava flow that's very, very hot and very runny and cools extremely quickly, we have a material called obsidian, which is a natural form of glass. And this knife, it was found in a Mayan tomb, dates to about 1100 AD. And by the way, it's quite sharp. When the person who found this, I understand, picked it up, he didn't realize it was laying on his hand and actually cut him. So it's very, very sharp. In fact, just as an aside, surgeons have tried using obsidian in surgery. Works very well and with less scarring. Okay, so it's something of a curiosity. The historian and philosopher Pliny attributed the discovery, accidentally of course, to Phoenician sailors. He recounted in his works how they landed on a beach, propped up a cooking pot on some blocks of a material called natron. It's now known, of course, as sodium carbonate. And they used it as cargo. In this case, they made a fire under it, and they cooked their food. The next morning, when the fire was out, they're cleaning up, they found naturally occurring glass, they thought. It turned out they had created it. The sodium carbonate, natron, had actually reduced the melting point of the glass of the sand around it, forming glass. Okay, now early lenses, however, were not made of a glass material. This is the Nimrod lens. It was made from quartz crystal and dates to about 700 BC. You can see time has not been kind to it. It had to be cemented back together from several pieces. But we believe this is one of the first really good examples of a practical use of optics, probably as a magnifier, like we use today for a reader. Other lenses were made from precious gems. Nero, legend at least, says that he watched events in the Colosseum through a lens of emerald. He must have had some kind of bank account for that, I'll tell you. Okay, optical discoveries over the years. Euclid wrote of the path of light through glass and water about 300 BC. One of the more notorious things here is Archimedes, of course, designing burning mirrors to set ships afire to help defend the city of Syracuse between 2014 and 2012 BC. Now, those of you who watched the original Mythbusters might remember that they tried to set a model aflame. They got the temperature up. I think they did it 2 or 3 times. Sometimes it succeeded, sometimes it didn't. They had the right materials, though. Archimedes was, according to this, had worked with burning mirrors which were made out of bronze. Bronze is a very high reflector in the infrared, so any energy from the sun, if you could hold it steady long enough, could probably do some kind of damage. Maybe not set fire to the ships, but you could blind the navigators as they head into the rocks. Nasty. Hero of Alexandria described the principles of reflection around 55 AD, and to the bottom there, a rediscovery of optics in general. Alhazen was a Muslim scientist, and he gathered all past written materials together into one anthology called Of Optics between 1045 and 1065 AD. Okay. After the 1204 fall of Constantinople, Turkish craftsmen fled to Italy, and particularly to Venice, to practice the art of glass manufacture. And it worked out pretty well, except for one tiny problem. Venice was mostly made of framed wood, and here you have these furnaces that are up around 1500, 1800 degrees Fahrenheit. You're asking for trouble. So in 1291, as a precaution, the town fathers moved the glassmakers and their furnaces to the island of Murano. Here they perfected the art and science of glass manufacture and casting to heights never before seen. You can still buy this stuff today. It's incredible. Absolutely beautiful things like 18, 20 generations later. So this is how they make it. Essentially, they have a melt, as it's called. Usually they start with a clear glass. They'll add various materials down to the bottom over here, colored glasses, so you can get a different pattern. They refire it, and they blow the glass through these long tubes. And some of the stuff is absolutely beautiful, stunning. Okay. Now, besides the blown glass and besides paperweights and vases that they made, there was one glassmaker in particular, Angelo Baroviere, mixed seaweed ash into the glass melt. Now, it sounds kind of funny. Why would he be doing this? The answer is quite frankly simple. He was trying to find out what would happen if you added different materials to glass. Would you get a better color? Would it be more transparent? It turned out it was extremely clear because, you see, the seaweed had potassium and manganese in it. And those elements came up with an extremely clear glass. It was dubbed in Italian cristallo, or crystal. This inspired other researchers to look to make better glass and predictable properties. Okay, now here's where I think there was a bit of a conspiracy, okay, ladies and gentlemen. I'm getting a little bit on in years, as a number of us are, and I had these glasses in front of my face. These aren't even glass, these are plastic. For, I don't know, it's got to be well over a half century now, ouch. Well, this guy, I think, invented something along with the printing press. This is a modern interpretation of the Gutenberg press. The printing press in the 1440s sparked an incredible revolution of literacy and of study. But then it also pointed up a problem. Most people, especially as they age, even today, were farsighted. So you couldn't read the book that you just spent a lot of money on. Eyeglass shops flourished as demand for corrective lenses increased. And it is my personal opinion that Gutenberg not only created the printing press, spread the word of knowledge around the world indirectly and directly, and he also invented font size 5, which I cannot read anymore. So I keep wondering, those are a conspiracy, but you never know. Okay, now this is actually one of the first depictions of glasses in 1342. And you can see that he's basically has them perched on his nose, and we were able to adjust these lenses so it would kind of pinch and hold. Okay, but not just lenses started to go into demand. The ideas of the uses of optics, though, were also growing throughout Europe. Okay, now maybe early inventors worked on here. Here we start getting into telescopes and instrumentation. In the 13th century, Roger Bacon wrote of the possibility of using lenses to see distant objects, but there's no evidence he actually made a telescope. And to the bottom here is the earliest known illustration of a telescope, and Della Porta included the sketch in a letter that was written in August of 1609. Okay, but before the telescope was born, if you will, a couple of years before, the microscope actually came into being. This is Anton von Leeuwenhoek. His microscopes magnified as much as 200 power. He was discovering life in drops of water from a stream. He was able to see cell structure. And he had created, I believe, up to 200 of these microscopes and such. Basically, if you look up to the top right here, you see there's a lens which basically was manufactured just by taking a glass rod and melting it and letting the droplets fall. They cool quickly in the air. You could cut them in half. We don't know quite how he polished it, but we do know that his work did magnify as much as 150 or 200 power, maybe more. There was a screw, you can see there, a specimen holder, and that allowed it to move up and down to get into the field of view of the lens, and an adjusting screw. And then, of course, you had other adjustments as well. And basically, this depicts von Leeuwenhoek using sunlight to magnify whatever you'd work. Now, at the bottom, that is not one of his microscopes. When he passed away, the Royal Society in England was bequeathed, I think there was about 30 or 40 of them. Unfortunately, they were made of silver, and that's a relatively precious metal. And for some reason, many people, no names mentioned, of course, in the Royal Society borrowed them, and they never came back. So this is a modern replication of it, and it works. It works fine. Okay. But then we have this, a little more complicated. This is Zacharias Jansen's compound microscope using lens systems. A lens in the front, the objective, and the eyepiece lens back here, and its particular setting and spacing, depending on what lenses you were working with. This is probably the first practical microscope, about 1595. Okay, now the official inventor of the telescope, this is a lot of controversy here. Hans Lippershey, an optician from Holland, applied for a patent of his optic tube, as it was called, on October 2nd of 1608. And at the same time, about 7 other people also walked into the court and applied for it as well. And this is his signature down here. And a description, which I cannot read, or anybody can do that, please do so, because I don't read Dutch anyhow. But it's a description of how he had put 2 lenses together at particular spacing. Other people made claims to it. There's a lot of controversy on it, but he was the first one, apparently, to at least sign and date the paper. And as working as an optician, not this type of optics, folks, but precision optics, laser optics, telescope mirrors, such like that. I always said on October 2nd there should be a holiday for opticians, a paid holiday. Okay, I tried getting that past my my boss, and Lee, I must have caught Lee at a really good time because he started laughing, was rolling on the floor, cracking up, and I said, okay. Every time I asked him about him, he didn't like that. I don't know. But this is amazing that we actually have this document. Now, the legend is, and you'll read this forever, that Lippershey's children actually were playing in Dad's shop when they chanced upon putting 2 lenses together. And suddenly the church in the distance was like about 3 times closer. And of course they squealed and jumped around, let me look a whole bit. Dad comes in, chases them out. They shouldn't be in the optical shop anyway. Kids are gone. Takes the lenses, looks at it, and says, if I put this in a tube, this might have some kind of a really good invention. Most likely, though, it was the results were from a lot of experimentation and his own knowledge of optics, but I still like the idea that the kids might have helped somewhere. Okay, by May of 1609, Galileo had learned of the new invention and taught himself how to grind and to polish lenses. He determined to use the new instrument to make his fortune, and he actually presented it to various burgomeisters and became quite popular, actually. He was then called, he went to a dinner at Rome, and he was called by no less than the Pope at the time. I think it was Pope Pius V. And he was a little concerned that maybe this guy who was pretty much ruled by his religion, his beliefs, might give some trouble. Instead, he said that your work is the gift of God, continue with your studies, and good release there. Also at that dinner, the first name came for it. Until this point, it was called perpextilium, or be able to see clearly. At that dinner, it was actually named the telescope, to see far. And by the way, one of the seeing fars would be to look, this is how Galileo really became popular. you could see a ship coming in, and it could raise flags at a distance that the human eye, the unassisted human eye, would not be able to see. And the flags would be different colors, and then your friends on shore would know hours before what you had in your hold, so you could set your prices and undercut everybody. Talk about cutthroat. Okay, but the first observations work. It's one of these incredible things where he's got fame, he's developing fortune, the whole bit, and then in Florence, he looks up at the moon, at a crescent moon, on the night of November 30th, 1609. This should be an astronomer's holiday. Okay? A new age began. From that balcony, Galileo first viewed a celestial object. He asked the very fundamental question, what would the moon look like in the telescope? These are drawings taken at the eyepiece by Galileo. They were gathered into a book called the Sidereus Nuncius, the Starry Messenger. And he talked about all the discoveries that he had made with the telescope. We had a lot of trouble over the years trying to figure out just exactly what he was looking. Was he actually looking at a last quarter moon, such as over here, or a first quarter moon, thinking that it was the entire moon? No. The field of view is so narrow in his best telescopes that, quite frankly, he was only looking at a section of the moon. Once you do that, then you can match it to the modern maps and photographs perfectly. And everywhere Galileo was looking was new and completely unsuspected. To the bottom here, you'll see there is a large disk and several little dots nearby. One night he saw 2, then he saw 3, then he saw 4. And apparently, over a period of nights, he was able to see that they were actually circling around Jupiter, like our moon goes around the Earth. This is the first major discovery with the telescope. And this is in his own penned in his own hand. An incredible thing. Now, fast forward to 2009, the Franklin Institute hosted the one and only time that I know of, at least, that a museum in Italy allowed the one remaining fully operational of his 4 telescopes to be here in the United States with a lot of other instruments and such too. And I went out there, and this thing was set up, this beautiful telescope's about this long, and it was set at about a 45-degree angle. And you know, everybody that came in to the museum had to look up. I did too. We didn't see anything. You couldn't get close enough to the eyepiece. But it was amazing to be able to at least get in line with the same instrument Galileo used. Incredible. Okay. Now, a correspondent with him, Johannes Kepler, who came up with planetary motion rules and regulations, if you will, he corresponded with Galileo in 1611. He modified the eyepiece to the modern design used today, which makes the telescope a lot easier to use. Not every instrument is a custom instrument now. You can interchange eyepieces, which means you could also change magnification. Okay, but problems with the refractor, which is the formal name because it uses lenses to refract light to a focus. When others scaled up the diameter of the objective lens, after all, Galileo's biggest telescope had an objective lens only about the size of a quarter. So what would happen maybe if you had 2 inches, or even 4 or 5? Well, when they scaled it up, it also scaled something else up. It's a property of glass to refract lenses differently at different colors. It's called chromatic aberration. A cheap telescope will show you bright color fringes around an image of anything, and that reduces the contrast. It distorts the image. To compensate, you had to make that objective lens with a very long focal length. It's distance from the objective lens to its focus. And the longer the focal length, the better the image became, but it also unfortunately got a little hard to handle. Like this. This represents a tiny image there of Johannes Hevelius in Gdansk, Poland. He made the longest, at least that we know of, that was operational. The lens was 4 inches in diameter, but it had a focal length of 150 feet. Now imagine you're on top of this roof. You're looking, you got it now, okay? You get this. You're trying to look at an object there, and a slight breeze goes by. Suddenly the image is going back and forth. You know, it's one of those things, okay, here comes Saturn. Oh, okay, it's gone. And yet he still was able to put together an incredibly detailed map of the moon. It was actually published after his death. His second wife, Elizabeth, who was not just his assistant but also an astronomer in her own right, they worked together as a wonderful team. But imagine trying to work something like this. So Christian Huygens, we're back in Holland again, developed a lighter and more manageable mount for the objective and eyepiece and kept the focal length under about 100 feet with a diameter about 3 inches, and with modern computers we say, yeah, it's for its time, for its design. That was about the optimum. And he set up what he called an aerial telescope and connected it together, as you can see, by a cord to the objective lens to the top of the pole. It's still awkward, but not so awkward that you couldn't make discoveries like this. He looked at Saturn. Saturn to Galileo was a puzzle. Sometimes in his little telescopes, it looked like just a disk. Sometimes it looked like it had ears, as he called it. He just could not figure out what was happening with Saturn. Well, Christian Huygens was able to discover that the planet was surrounded by a ring nowhere touching the planet. And that aerial telescope not only allowed him to be able to see that, it also got rid of another mystery, why Galileo didn't see the ears or protuberances or what have you every about 14 years or so. It's because the aspect of the rings changes as it goes around the sun relative to Earth. So sometimes, like now, coming up in summer, where we have 3 planets coming in, we'll talk about that some other time. But sometimes the rings will be presented wide, sometimes they will go on edge, and then you see the other side and back and forth over a period of 29 years, a full cycle, which is, of course, Saturn's revolutionary period around the sun. So it's just the way we looked at it. But he also discovered something else. Saturn had, at the time, 1 moon, Titan. And interestingly enough, that also has an atmosphere. That's for another lecture sometime. Okay, in his book Optics, I always said that if your book gets reprinted by Dover Publications, you've made it. Well, you can get his Optics today, even Principia, I believe, his real, what I look at least, as the foundations of modern physics. Newton correctly deduced what was happening to light when it went through a lens. Think of a lens as a prism with the bases top to bottom. White light goes through, it refracts depending on the color, and you end up having a nice rainbow, but unfortunately that's not what you want when you're looking in the eyepiece. So he said, let's minimize this completely. Let's put little baby lenses in there. We still need them for the objective so we can magnify it, but instead of gathering it by a lens, let's use a concave mirror. And this is the original Newtonian telescope, where you have a mirror to the bottom, they're a little larger than a quarter, had a focal length roughly about this long. And with the eyepiece there, it magnified 30 power, which is about what Galileo was working with. So this is really incredible. Okay, now John Hadley took his design some years later and created a telescope that most amateur telescope makers, amateur astronomers can build themselves today with modern materials. This had a 6-inch diameter, and a focal length of about 62 inches on a mount which had slow motion controls, and he presented it to the Royal Society. This was like you or I being given the keys to the Enterprise E, and you were able to just basically end up exploring space, which is exactly what this telescope and others after it followed. This was an amazing piece of equipment, and any amateur can build something like that today. Okay, 2 other people, an Englishman and a Spanish gentleman who is an artist, actually. This is John Gregory. His Gregorian telescope, because the design required 2 concave mirrors, they're rather easy to make. Sierra Cassegrain came up with a system by which you have a large primary mirror, but then you also have a secondary mirror which is convex. Newton never minced words, especially when he was trying to, shall we say, make sure people knew where their place was. So he looked at this Cassegrain telescope and he said its advantages are none. And I frankly believe that the difficulty in making that secondary mirror will mean that this telescope will never be built. Well, Cassegrain was an artist and a writer and a scientist. He said, okay, well, if that's what Isaac says, fine. Okay. We don't know very much more beyond that. Interestingly enough, though, that design, the bottom design there, is the one that most major telescopes in the world are built, including the Hubble telescope and the soon-to-be orbited James Webb. Our 26-inch telescope here is of the lower design. Okay. One of my personal heroes, William Herschel. He was a German-born English optician and astronomer. He is also called the first observational astronomer as well. He built the largest telescope of its day. You see it in the background, this wonderful painting here. That is a 48-inch telescope with a 40-foot focal length. The instrument next to it on a frame is probably not the actual telescope, unless I think this came from, if I remember correctly, from the London Science Museum. The actual Uranus telescope is, I understand it, is in the Adler Planetarium in Chicago. How it got there, I'm still trying to figure. But he was an amateur astronomer, he was a musician, and his study of sound led him into the study of light, and he got hooked bad, tight, like you couldn't believe, on astronomy and observing. He made over 200 mirrors in his time, and this is a replica of one of his favorites. Well, let's put it this way. He even said that the telescope that gives you the most information is the one that you use the most. So if you have this big monster telescope, it takes 3 guys to work it, that's not going to give as many discoveries as a 6-inch instrument like this. And he was able to use a telescope similar to this to discover the planet Uranus in a survey of the night sky. Now, it's really an incredible piece of work here. You're seeing a family over here. Of course, William over here, roughly about age 50 at the time. His young son, John, who would help astronomy, and most importantly, would be able to... okay, we have more people coming in. Come on in. Okay, better late than never, folks. The whole thing here is that he worked with these telescopes in his surveys, but that was all visual. John helped in early photography. He even created the name photography, the snapshot, and fixer and developer chemicals. He was actually trained as a chemist. The young lady whose face we do not see over here is Caroline, Lena, that was his sister. And William and Caroline surveyed the night sky, creating what he called the general catalog. She herself discovered 9 comets, and I think that's about right, yes, and a number of deep sky objects that we know today. What a lady. Okay, so a little quick view on history. Now we're going to talk about a little optical principles. Don't worry, folks, you're not going to get math. There's no test involved with this. However, the mathematics of this is absolutely beautiful. This shows what glass can do. This is refraction. I've mentioned that before. It's the changing of the path of light as it passes from a medium of low density to that of high density. The angle can be calculated with extremely high accuracy, which means you know where that optic is going to send the light, which means you can predict. That's the beauty of science. It isn't just pure guesswork. We know how something will be, and we can prove it over and over again. That is how science works. And this illustration on the right is a beautiful example of what is shown here in diagram, because you can see the light coming through, it's bent, and it comes back out almost exactly parallel. It's absolutely beautifully done. Reflection, of course, is the changing of path of light by a highly polished mirror, and it depends on the flatness or curvature of that mirror where that light will go. Again, you can predict where it will be. And this is one of my favorite photographs in the entire set. This just demonstrates dispersion, which is the bending of light through a refractive medium, glass or crystal, depending on the wavelength of light. It's the cause of that chromatic aberration I mentioned before in ordinary refractors. But take a good look at this. Here you're seeing total reflection of light here, refraction, and then dispersion, bringing it into different colors. Is that incredible in one photo or what? Okay. And diffraction, due to the wavelength of light, waves of light can be made to break up into dark and bright bands, constructive and destructive, as it's called. The light waves actually interfere with each other. Diffraction and interference of light are virtually the same. And they interfere with each other as they pass through an aperture or surface in their path, which explains sometimes when you have a not very good telescope and you look at a bright object, you'll have color there, but you also have some rings around it that aren't quite evenly illuminated. That's because it's being diffracted or scattered. Okay. Later on, new materials and better designs. This is Pierre-Louis Guénand, who worked for Utzschneider Limited in Germany. And he developed the chemistry and physical methods of producing high-quality flint glass. That's a glass that has a very high index, a very high ability to be able to bend light. It contains lead. Even today we still use it, but now our chemistry is getting good enough so we can reduce that, so it's safer for opticians and for people who are working with the glass for that matter. But his methods of producing high-quality flint glass was very, very simple. Because you have that lead oxide in the glass, they used to take a wooden stirring rod of oak, plunge it into the melt. It would carbonize, it would burn and carbonize and protect the rest of the wood, and you would stir it. But if you remember your basic chemistry, lead oxide and carbon yields lead and carbon dioxide. And that lead separates out and makes all sorts of little striae and strings and ruins the melt. You could have 100 pounds of glass made, and only about 20 pounds would be usable. Until he came up with a different method. The biggest piece of glass you could make accurately repeated, but it's about this big. When he learned to take that same rod and then cover it with fire clay, now there's no oxidation. They were coming up with objects 8, 10, 12, 14 inches in diameter and bigger. And he was to train, he didn't want to do it, but he did anyhow. He was paid for it. That's what the boss says, to train a young man in these techniques. This is Josef Fraunhofer, a young optical engineer and glassmaker of a family of glassmakers. His grandfather and father and he all worked on this. They further developed this formula for making the pure glasses that were needed to make the finest of 19th century refractors. This is in honored retirement. This is the Great Dorpat refractor. It was completed after his death. But this instrument originally, that wood tube shone in mahogany, shone like polished brass. And if you would walk over to this telescope and move it in its heyday, you could just touch it when the locks are off and it would just quietly move back and forth. And it had a falling weight drive as well. This is what we call now the German equatorial mount. Okay. But in his work to make these larger optic sets and such, he studied the property of light itself, inventing what we call today the spectroscope, or magnifying, viewing the spectrum or color, which led to the beginnings of modern optical design. And basically it shows him standing, demonstrating with this instrument to be able to look at light and be able to see the various colors and get a very accurate work. He wanted to see what was happening. So he put a magnifier on that rainbow. And he measured how different wavelengths of light were refracted or bent by optical glass and created the first multi-wavelength glass tables. And he used that to design better achromats, color-corrected lenses. Although we don't know the calculations, that is the beginning of modern optical engineering. You can go to any optical company, Hoyer, O'Hara, Schott, any place that manufactures glass, you can get these tables in a book, or you can get them online. And it's not just for red, blue, and green, but for a number of colors. When he looked at the solar spectrum, he saw up to 540 lines. I believe that's about right. Yeah. Well, he did not understand what was happening with these lines, where he figured maybe they were spacers in light. He died at the age of 39, unfortunately, because of those glass mixtures. They used not just lead, they used arsenic, antimony. They tried all sorts of experiments to see what they would come out with. Unfortunately, he poisoned himself, in effect, with it, like his parents before him. But finally, some years after his death, Gustav Kirchhoff, which is the gentleman over here on the left, and on the right, Robert Bunsen, cracked this code with the better designed spectroscope. The elements that comprise the sun were the same ones that were found here on Earth and later on other stars as well. And then other researchers discovered that an object's speed and direction could be determined by the light it emitted, the Doppler shift. If you ever heard a car go by, the sound, that's Doppler shift. If you were in the car, you just hear, but because your reference is changing as the object goes by you, that happens also with light. It affects how the light is received by you. If the spectrum is shifted a little to the red or to the blue, going away from you, coming toward you. Okay. The dialytic refractor, very important for today. In 1828, Alexander Rogers proposed a subaperture corrector. He still didn't get the proper sized flint glass yet. You can make small ones, so he put a corrector in there. That's what we call this today. This led to the modern ultra-achromats like the Televue Renaissance and other refractors. Televue, Uncle Al Nagler, as he's called, I think he just cracked 80 just recently. The guy's fantastic. I've been watching his career and his work from the early 70s. An amazing gentleman, wonderful person to talk with, and smart as a whip. He rediscovered this principle with modern glasses. You can't get better refractor telescopes. Okay, von Liebig and Foucault. Von Liebig, Justus von Liebig, is more known as a chemist that discovered how to add fertilizer, chemical fertilizers, to the soil. So instead of one person being able to eat in a given area, maybe 30 or 40 could do so. Also, Foucault was able to invent a laboratory test in about 1858. So between the two of them, between Foucault being able to accurately measure the surface accuracy of a piece of glass rather than metals, which are highly reflective, sort of, about 64%. Now, von Liebig came up with a way of chemically silvering. Suddenly, your one mirror, instead of reflecting about 64% of the light, could reflect as much as 95%. That means your reach into space goes that much easier. Okay. Photography, as I mentioned before, John Herschel and others worked on photography. This is Delarue's photoheliograph. Once a day, he would photograph this large instrument. The sun. First time we had a permanent record instead of just having drawings, although drawings still are valuable. And William Huggins' spectrograph was starting to mine the stars to try to see compositions and maybe even classification of stars by that method. In the United States, the Clark family, true artists in glass, the Clark family made the largest refractors in history, up to the 40-inch at Yerkes Observatory. This picture was taken in 1929. Anybody recognize this guy in the front? That's right, it's Albert Einstein. He was on one of his visits, and he went to the Yerkes refractor. And that's a wide-angle shot of another instrument that the Clarks did. A little one, smaller one, it was 36 inches across. That's in Lick Observatory in California. Okay, and this is an almost forgotten design. Ludwig Schuppmann developed a design that gave total color correction using only one type of glass. Before you had to use crown and flint or different combinations. In this case, it's all the same glass from the same melt. That's the secret. It's all the same compositions. It's a good friend of mine in the front there, Cliff Ashcraft, with his telescope that he had built. I think that right now on Earth, thanks to amateurs, it's the most number of this design at any given time in history. And we've rediscovered the work and created the high quality examples of it. Absolutely beautiful piece of work. Okay. And then we start getting into the world of giants here. This is George Ellery Hale, the inset there at the right. He repeatedly built large telescopes. He found the funding to create the 36-inch and 40-inch refractors I just mentioned, and then the 60-inch from left to right, the 60-inch, the 100-inch, and 10 years after his death and after World War II, the 200-inch telescope, a 5-meter instrument. Now, if you go up to Corning, New York, to the Corning Museum, you will see the rejected blank for this because, quite frankly, the melted through the iron bars that were holding the framework for the network of Pyrex. But it's still beautiful. Sometimes, if you're lucky, you go by at night and they backlight the almost 17-foot diameter mirror blank, and you see all the ribbing inside that reduced its weight dramatically. Not as dramatic as we do today, and we'll get to that in a moment. So this, Hale himself should have his own lecture. Maybe one of these days I'll do that. But he did an incredible piece of work here, organizing, moving, motivating, and extending our view into the universe. Okay, the Stellafane. How many people have gone to the telescope making convention at Stellafane? I have. A couple people have been up there. Okay. Stellafane, or Shrine to the Stars, as the name implies, is up in Springfield, Vermont. This building that you see here is a telescope and a mounting, because the optics are built into it. There's a 12-inch telescope mirror with a large flat that gathers light and brings it inside this heated or cooled, depending on the season, observatory. See, the gentleman on the right over here, Russell Porter, was an Arctic explorer in his youth, and he did not want to be in the cold, even the somewhat warmer cold, if you want to call it that, of New England, because he was stranded on the ice with people for about 2.5 years. So he said, no more of this. So he ended up with a heated observatory. Lucky guy. Today, at the Telescope Makers Convention, usually it's toward the end of July, early August. This is a place where you see innovation all over the place. The background there is the famous pink clubhouse. It was supposed to be a light spruce, and somebody added a little too much spruce to the light. And it's been tradition to keep it that color, and I think it's great. But James Harkness is on the left here. He was a former governor of Vermont. They worked together to build Stellafane, and Hale heard about Porter, and he realized he was an artisan and engineer. And Porter's drawings, cutaway drawings, you can see now in almost every astronomy book, and it shows the 200-inch, showing the engineers and the common workers and everybody in between how the telescope worked. Beautiful cutaway, had a gift for that. There we are, as the engineer. And on the upper right is a Schmid Cassegrain, a Schmid camera, excuse me. That instrument just recently was upgraded so it can continue its work many years after its building. And of course, this is the prime focus cage, as they call it, for the 200-inch telescope. Literally back then, you rode the telescope as it moved across the sky so you could guide on a photographic plate. I think the last time they did that was in 1996, I believe, or 7. Now it's all computerized, and it's not film anymore. It's a charge coupled device, a CCD device. How many people here have a digital camera? I know, silly question, right? Good. The people who invented that got the Nobel Prize for the charge coupled device. And it started actually as an experiment where you only had 8 pixels for the image. When they put an electronic version of this type of camera on the 200-inch, it was a dream of one of the engineers that worked at least on some of the larger telescopes, where George Willis Ritchie predicted an electronic telescope could be built that would be 200 inches across, but have the light gathering capability equivalent of 2,000 inches. And it did. Okay, now in the modern era, this is Dr. Roger Angel of the Muir Lab at Stewart Observatory, University of Arizona. And this is the spinning oven. When they first did this work, they actually had a guy that would ride on this thing on a very precise bearing, where the oven, where this was being fused together. You can see, I'm going to move off the camera for just a moment. You can see inside the oven how it's glowing hot, while all these sections here were all fused together into an 8-meter mirror. That's 8 meters. That's bigger than the 5-meter out in Palomar. If we had that mirror here, we'd have to kick the walls out, because 8 meters is roughly from behind me, actually through that wall and out. So we're talking 1 mirror that big. And they're able to make these maybe, I think it's every year and a half, thereabouts, because you have to cool it down properly, and then it has to go through optical processing. We'll talk about that in a moment. And you can see how big that thing is. Now, if this was a solid piece of glass, it would weigh well over 100 tons. This is not quite 8.5 tons. And it's just as stiff as that solid piece of glass would be. Here, this is how you make a mirror. You make a mold, and you pack very, very specialized glass, E6, like Pyrex, but much purer chemically. And you put it in the spinning oven. And of course, everybody wants to, mug for the camera. So in the upper right, there's a lot of the people that were involved with it. And then processing for a telescope that's coming online pretty soon, the LSST, where this very complex piece of equipment This is the primary mirror, the secondary, the tertiary mirror. 3 mirrors, 2 of them in one. This is incredibly precision optics to get everything centered just right. And this is it, the Large Synoptic Survey Telescope. It's supposed to go online, I believe, next year after next. It'll image the entire sky visible from where it will be in Chile every 3 nights. It's going to produce 100 gigabyte of data in each image. We're literally drinking from the fire hose in data. And to give you an idea of the size of the CCD camera, take a look at that. That's a simulation of the composite of all the chips put together to make one camera. And that's the size of the moon. That's a half a degree. So this is going to be a huge piece of equipment. And we're going to be processing this data well into the 23rd century. Okay, bold engineering. No longer do you have to make, the joke was, you make one mirror, you breathe a huge sigh of relief, and don't do it again for 50 years. Not anymore. Here you have the large binocular telescope, and before you ask, no, somebody doesn't stand there and look through like this. They are 2 telescopes mounted tandem. One's for visible light and one in infrared, so you can photograph in both wavelengths. Gemini North, I had the privilege of working on some of the optics for the prisms that went into the spectrograph for this. This again is another lightweight mirror, and it is Gemini North, as the name implies, is in the northern hemisphere in Hawaii. Gemini South is in Chile. Incredible piece of work, and these things, if you look how spindly they look and you compare them with the 200-inch, you can see that the engineers finally got enough courage to say, well, yeah, they do have strength of materials, and we can compensate for weights, especially if it's all lightweight sections. And a computer can drive it. We don't need an equatorial mount anymore. The computer is able to move what's called an alt-azimuth telescope, the common one that you see where you look up and down and 360 degrees around. And it can track the sky beautifully. And multiple mirror telescopes. The original multiple mirror telescope used 6 Air Force surplus 72-inch mirrors to combine into one image with a 36-inch telescope mirror in the center. That has been replaced by one 6.5-meter mirror. I don't know what happened to the other 6 mirrors. Maybe the Air Force wanted them back, who knows. The South Africa Large Telescope is made up of tiles of glass and coated, but it is not the first. The prototype is the Hobie Eberly telescope that's down in Texas. And this instrument, you do not ride, you do not put a camera per se on it. You take the telescope and you move it to where you want to view. You put it down, you hit the brakes, put it down. And then there are detectors at the top of the telescope there. You see them in black looking out there. That detector is what moves across the sky, following it across. Same thing with the SALT telescope as well. This is incredible engineering. Without computers, you would not be able to do this. And then future telescopes, this is coming online soon. The Giant Magellan Telescope brings the power of 7 8.4 meter mirrors together to make one giant equivalent of a 16-meter instrument. Incredible piece of work. And that's a model, gives you an idea of scale. Look at that full-size truck over there. So we're talking big optics, big telescopes to solve the big problems about where the universe came from, how did it come into existence, why is hydrogen, helium, lithium, and a tiny trace of beryllium and boron created from the so-called Big Bang, the creation event, whatever you want to call it. How far can we see? What is the brick wall, if you will? These help to solve those problems and maybe create others in the process. The 30-meter telescope is currently being funded, which hopefully will have completion around 2022. So the young people in here are going to be seeing some incredible sights. And the European, I love these names, European Extremely Large Telescope, not to be pushed out of the way, 42-meter aperture. That's half a football field size. They had a telescope, was called the Owl. Overwhelmingly large telescope. Oh, God. Well, they're not building that one because that turned out to be a little too difficult. They couldn't get funding, which is a shame. But just as a comparison, this is the story so far. Various telescopes, some that are mirrors, some that are tiles of mirrors. And in the background was the discontinued, the white disc there is the overwhelmingly large telescope which exceeds all of them, but unfortunately has not been built yet.
Yeah.
May never be. You never know. And then future amateur telescopes. These pictures are about 15 years old. We've gone well beyond them. On the right is a Dobsonian and alt-azimuth telescope with an early laptop driving it. So you could photograph and image process at the same time. There was a NASA engineer that came up there about 12 years or so ago with a 32-inch mirror. You can see it right here. That's only this thick. And it's not made of glass. It's made of carbon composite. So these little tubes are holding these two 1/8-inch thick surfaces. It's called replicated optics. You have a form, put a release agent, put epoxy on it, plop this form behind it, let it harden, pull it off, illuminize it, and keep on going. These hands held that 32-inch mirror. He had a prototype that we could handle. That prototype only weighed about 4 pounds in my hands. If that were glass, let's just say my hands wouldn't be here. They would have been on the ground and probably crushed because they weigh well over a ton. So here we're talking extremely light optics. Okay, and how it's done, I'm going to go through this rather quickly because the math is basically how to design lenses. Anybody's really interested, I can send them these through the web, this information. But basically, you specify the crown and flint glass for this achromat. You can derive the radii of the lenses and such. Then you go to the storehouse and you find the glass that matches the design formulae. And you cut them up on diamond saws and to square blanks and then edge them to diameter. And then the glass is blocked and generated by diamond generating, close to thickness in the radii that you need. And then you block them with a special pitch and an iron mounted on an iron tool, which you use it to grind into the radius. And sometimes it's easier and better to hand polish an optic. I've done it quite a bit, actually, of my career. A large set of lenses to start. But sometimes it's really nice to let the machine do the job. Especially when you got all these little lenses. There's 3 in a block over there, and you can get maybe about 30 at a shot per hour. By hand, you're doing maybe about 2 or 3 an hour. Okay, and always busy. This is when I worked at Lytton up in Morristown. The machine that you're seeing over there is an overarm machine, very standard. And the pitch lapse you're seeing with the optics in both these cases here face down onto the pitch. And the compound was, back then, I was using an application with a brush. Okay, when you would test it, you put it into interferometer, something relatively simple if need be, basically putting an optical flat on top of whatever you're polishing in this case, or if it's a radius, what's called a test glass. And you get interference of light with a single color light as you're seeing here. Okay, but believe me, it's nice doing interpretation. But there are all sorts of elements that get in the way. You can't get quite on top of the optic to be able to see the interference fringes and just how straight they are, the angle affects it, the light, everything. Witness computerization. This is a Zygo interferometer. Now I work with a big brother of the old Mark II over here, the Verifier, and incredible piece of work. Takes the guesswork out of it. And a messy desk, however, is a sign of genius. This is my workstation, or what's left of it, when I was at Optics for Research. You can see one of the test lights, the green square in the background there. Camera equipment, you name it. We had a melting table over there. Next to that, a blocking table. So everything is orderly. You go from the blanks to the finished blanks to the polishing to the figuring, and then into cleaning and inspection. Okay, and the never-ending battle. This is a Wiesbecker machine, 6 spindles, and very unique method of working. One big, humongous 3/4 to a full horsepower electric motor to make these optics move back and forth. Off on the far right, framed in blue a little bit over there, that is a treadle machine. It's a pedaling machine, where you would sit there, you would stand in on a chair and move your feet back and forth, which would turn the spindles, and by hand you would move this back and forth. You could hit 20th wave very nicely with that. And new technology on the horizon. This is not really new. If you have a telescope which is called a Schmid-Cassegrain, and you have that window. Those glass windows are made initially on this kind of machine, which is a CP, or continuous polisher, and you have a bruiser plate, which basically keeps that ribbon, if you will, of pitch flat. So you come up with good blanks, and from there there's a proprietary method of shaping it to what the Schmid-Cassegrain needs. Okay, and this just in. Okay, everybody probably by now has seen Star Trek IV, I would hope. You know, the movie Star Trek IV, The Voyage Home. And Scotty and Dr. McCoy go to a plastics manufacturer, and they teach him how to manufacture transparent aluminum. Now, back then we said, yeah, right, sure. Every optician seeing it said, no, no, no. This is not really glass, however. It's not transparent aluminum, but this is aluminum oxynitride. This is very new. This only came out about 2 or 3 years ago. It's bullet resistant and a third the weight of Kevlar armor. What you're seeing on the right is triple laminated glass like what we have in our armored Humvees over in the Middle East. And you can see there were 3 shots there, and it didn't get through, but now you can't see through the glass. In this case, this is a crystal, a single crystal. It has been hit with the same 38 at close range. I think it was about a meter away, 39 inches. You don't even see a scratch on it. And a layered version of this could be made into a pretty good body armor, not just for our soldiers, but for police, even for chemical reactions. You don't want your chemical reactor to blow up in your face. You want it to go out a particular way. This will make sure that that explosion goes directed away. And this is only the beginning here of crystal materials. So, after all this, what is glass? Glass is an invisible solid, a joyous and paradoxical thing. As good a material as any to build a life from, by Peter Carey. And I'll let you read this. This is Robert Goddard. When he was 19, he was valedictorian in his school up in, I believe it was in Auburn, Massachusetts. And it is difficult to say what's impossible, because it could become the reality of tomorrow. Same thing with the optical industry. Same thing with all the optics. I cannot begin to imagine what the future holds for my industry, and therefore for all of you, and those who are seeing me now. This would be astonishing. And I've only been doing this now, I think, last year, it was my 40th anniversary of doing this, and I still feel like my career is still starting. This is the longest credit I have of all this. These people are all involved with my life at one point or another. Some still are. Of course, my wife Bonnie, who did the production work on this, so everything is spelled right and centered. It's because of that young lady back there with the turquoise and gray suit. My late uncle, no, excuse me, not even him, my late grandfather. And he was my first guide to science. My mother, Rose Cascardo, who was the model for me becoming a teacher. She was a strict disciplinarian, but she kept me heading toward the sciences. Mary Duca, our AAI president. Aaron Zuckerman is now vice president. Michelle Toffel is a fellow educator and inspirer. Leah Coronado, a colleague and friend that kept me together for 20 years at OFR. Don Wilson, who owned OFR and created a new company. He retired 6 months and went back in the optics. Lee Stenikin, who's currently the president, a good friend of mine up at ESCO. John Bird, also production manager. Bruce Van Orden, I work with, a bunch of crazy people up there. The Springfield telescope makers up at Stellafane. Thing was, in August 6th of 1977, I'm rather proud to tell you, I took first award at Stellafane. Then that was on Saturday, on the 5th. On the 7th, I went into this crazy industry. All the observers at AAI, yeah, it is crazy. All the observers here at NJAA, and all the members of many other clubs I work with, which keep me going in the science and in the hobby. And with that, that's the end of our talk. I thank you for your attention. Okay. Now, I'll take questions. Okay.
Well, we often get questions about the machine underneath the telescope mounts there.
Mm-hmm.
Did it actually work? How long did it take?
Okay.
This reportedly was used to make our mirror.
That it did.
And I hear a kind of different story, so I would
Okay.
love to hear from you.
Okay. Unfortunately, when that mirror was being made, I was still in high school. I think it was a freshman, if I remember correctly. However, that is an overall machine. It's called a Draper machine, named for the optician that had developed it. It did work, that mirror. And they, you know, there's an older tape for NJAA where it says polishing, testing, polishing, testing. They're not kidding. They had to have to polish it maybe a half an hour to an hour, then let this big thick piece of glass cool for about 2 or 3 hours. And that did indeed make it work. And that machine, I'll tell you this much, I've brought 1 or 2 friends of mine that are in optics, and they'd love to get their hands on this thing for large mirrors. So it's not computerized. You just have to pay attention to it, that's all. Any other questions? One all the way in the back there.
That monster Herschel, was that the speculum metal?
That was all speculum metal, that's right. It's a high tin bronze. We still use it in the infrared. It's a wonderful reflector in the IR. But one bad thing, his alloy was easy to grind. It was a little bit softer than normal, but it tarnished. You blink your eyes. And now today, we polish it in rare occasions. We put it immediately into a vacuum chamber and overcoat it with quartz, and that lets it last maybe about 2 or 3 years, but eventually our wonderful polluted atmosphere, no matter how clear we think it is, gets through. So, okay. Now, as I understand, if there are no other questions, okay, I understand we have a tape we normally play?
Can you just kill that and run the video, please?
Okay.
Thank you.
Let's go to the videotape. Okay. And here we are. And I'll get out of the way here.